Merry Christmas. Today on Lessons in Dave Carrolls, as we enjoy 12 Days of Christmas but Every Verse Gets Jazzier by Charles Cornell, I will be reading from the Wikipedia article on large numbers. Enjoy. Large numbers. This article has multiple issues. It may contain an excessive amount of intricate detail that may interest only a particular audience. You have been warned. Large numbers are numbers that are significantly larger than those typically used in everyday life, for instance, in simple counting or in monetary transactions. The term typically refers to large positive integers, or more generally, large positive real numbers, but it may also be used in other contexts. The study of nomenclature and properties of large numbers is sometimes called Googology. How fun! Very large numbers often occur in fields such as mathematics, cosmology, cryptography, and statistical mechanics. Sometimes people refer to numbers as being astronomically large. However, it is easy to mathematically define numbers that are much larger even than those used in astronomy. Scientific notation was created to handle the wide range of values that occur in scientific study. 1 times 10 to the power of 9, for example, means 1 billion, and 1 times 10 to the negative 9 means 1 billionth, or 0.000000001. Simply writing a big 10 with a little 9 on its shoulder instead of 9 zeros saves readers the effort and hazard of counting a long series of zeros to see how large the number is. Thanks. Examples of large numbers describing everyday real-world objects include the number of cells in the human body, which is estimated at 3.72 times 10 to the 13th power. The number of bits on a computer hard disk is also typically about 10 to the 13th, between 1 and 2 terabytes. The number of neuronal connections in the human brain is estimated at 10 to the 14th. The Avogadro Constant is the number of elementary entities, usually atoms or molecules, in 1 mole. Its value is approximately 6.022 times 10 to the 23rd power. The total number of DNA base pairs within the entire biomass on Earth as a possible approximation of global biodiversity is estimated at 5.3 plus or minus 3.6 times 10 to the 37th power. The mass of Earth consists of about 4 times 10 to the 51 nucleons. The estimated number of atoms in the observable universe is 10 to the 80th power, and the lower bound on the game tree complexity of chess, also known as the Shannon number, is estimated at around 10 to the power of 120. Damn. I'm going to scroll down a ways here. The order of magnitude of a number on a larger scale than usually meant can be characterized by the number of times n one has to take the log in base 10 to get a number between 1 and 10. Thus, the numbers between 10 up arrow n and 10 up arrow n plus 1. As explained, a more precise description of a number also specifies the value of this number between 1 and 10, or the previous number taking the logarithm 1 time less between 10 and 10 to the 10th, or the next between 0 and 1. Note that 10 to the 10 up arrow to the n times x is equal to 10 up arrow to the n times 10 to the x. Okay, scrolling back up now. Apparently the longest finite time that has so far been explicitly calculated is 10 to the 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 1.1 years, which corresponds to the scale of an estimated Poincare recurrence time for the quantum state of a hypothetical box containing a black hole with the estimated mass of the entire universe, observable or not, assuming an inflationary model with an inflaton whose mass is 10 to the minus 6 Planck masses. Okay. This time assumes a statistical model subject to Poincare recurrence. A much simplified way of thinking about this time is in a model where the universe's history repeats itself arbitrarily many times due to properties of statistical mechanics. This is the timescale when it will first be somewhat similar, for a reasonable choice of similar, to its current state again. Here we go. Examples. The largest known Smith number is 10 to the power of 1031 minus 1 times 10 to the 4,594 plus 3 times 10 to the 2,297 plus 1 quantity to the 1,476 times 10 to the 3,913,210. The largest number Sen prime as of December 21st, 2018 is 2 to the 82,589,933 minus 1 1 millennium is either 10 to the 3003 or 10 to the 6000, depending on your number naming system. What a great name. Graham's number, click, is so large that the observable universe is far too small to contain an ordinary digital representation of Graham's number. Assuming that each digit occupies one Planck volume, possibly the smallest measurable space, but even the number of digits in this digital representation of Graham's number would itself be a number so large that its digital representation cannot be represented in the observable universe. Nor even can the number of digits of that number, and so forth for a number of times far exceeding the total number of Planck volumes in the observable universe. Its last 12 digits are 2624641953887.